So let's look at this function. Given that f of x is equal to the piecewise function 6 over x plus 2 plus e to the 5x when x is less than 0, 4 times cosine of pi x when x is between 0 and 1, and x to the 17th plus the cube root of x plus 6 when x is greater than 1, where is f of x continuous? So really, just like last time, when someone asks this question, they're really asking you, where is this function not continuous? Because most functions are continuous at most places. I will point out, so here's just a very incomplete list of functions that are continuous. Polynomial functions are continuous everywhere. Trig functions are continuous on their domains, meaning everywhere they're defined. Rational functions are continuous on their domain. Rational function, that's where you have a polynomial divided by another polynomial. Exponential functions are continuous everywhere. Logarithmic functions are continuous on their domain, meaning everywhere they're defined. So most functions, if they're defined there, they're usually continuous there. There are some exceptions. Usually they look piecewise, but most quote unquote normal looking functions are continuous the places where you'd expect them to be. That said, how do we identify where a function isn't continuous? Well, if I look at these three pieces, just the pieces on their own, I would point out x to the 17th, no problem there. Cube root of x, no problem there. Odd roots don't have any domain issues. Odd roots are defined everywhere. Odd roots are continuous everywhere. And plus 6 isn't going to change anything. So when you add a continuous function plus a continuous function plus a continuous function, the result is also a continuous function. So this piece down here is continuous everywhere it's defined. So is cosine. 4 times cosine of pi x. Yeah, you've changed the period and you've changed the amplitude, but that doesn't change the continuity. That function is also continuous everywhere it's defined. And lastly, this top piece, e to the 5x is exponential. It's continuous everywhere it's defined. 6 over x plus 2 is a rational function. It's continuous everywhere it's defined. It is not defined at x equals -2, which does happen to be in this particular part of where it's defined. So we can start off by saying, for sure, f of x is not continuous at x equal to -2. That is for sure something we need to exclude from our interval of continuity. Now, after you've looked at each piece and kind of seen if it might be discontinuous somewhere that's obvious, the other places we always look at in a piecewise function are where you change from one piece to the other piece. So the other places where we need to determine whether or not the function is continuous is at x equals 0 and at x equals 1. So let's start by looking at x equals 0. 3 things we have to check for continuity. Thing 1, does f of 0 exist? Yeah, it does, right? I can plug in 0 and I can get that f of 0 is equal to, I'm gonna plug it into the middle piece because that's where x is defined to be equal to 0, and get 4 times cosine of pi times 0. Pi times 0 is 0, cosine of 0 is 1. So I get 4 times 1, which is 4. And the second thing we have to check is, does the limit as x approaches 0 of f of x exist? This usually, especially for piecewise functions, means you have to check both of the one-sided limits. We already know what one of them is going to be. The limit from the side that uses the same piece of the function that we just evaluated is going to have the same limit. So it's not a big stretch to say that we know in this case, the limit as x approaches 0 from the right of f of x is going to be the limit as x approaches 0 from the right of 4 cosine of pi x. And then we would plug in 0 and get 4 cosine of 0, which is again equal to 4. Normally, I don't actually do that part. Normally, I go to the other side to see if things are going to be problematic or not. So I'm actually going to look at the limit as x approaches 0 from the left of f of x, which means I'm going to be using this top piece of my piecewise function. That's going to be the limit as x approaches 0 from the left of 6 over x plus 2 plus e to the 5x. And just like whenever we're trying to evaluate a limit, the first thing we're going to do is just try substituting in the value that x is approaching. If I plug in 0, I get 6 over 0 plus 2 plus e to the 5 times 0. That's 3 plus 1, which is 4. And since the right-hand limit and the left-hand limit happen to be the same value, that means the limit exists. So the answer to this question is yes, and it's equal to 4. And then the third thing we have to check, which should be obvious at this point, what the answer is. The third thing we have to check is, are these first two things equal to each other? If the function exists and the limit exists, do they have the same value? Usually when I do this part, I like to kind of answer the question overall. So I would say part 3, f of x is continuous at x equal to 0 because f of 0 is equal to the limit as x approaches 0 of f of x. You could also mention it is equal to 4, but you don't actually need to state what the value is. You just need to know that the function value and the limit value are the same number. And now we're going to do the same thing at x equal to 1. In fact, I want you all to do the same thing at x equal to 1. So check the 3 things for x equal to 1. So thing 1, you all are going to figure out what f of 1 is. Part 2, you're going to look at the limit as x approaches 1 from the left of f of x and the limit as x approaches 1 from the right of f of x. And then you're going to finally conclude whether or not things are continuous or not. In case you don't remember, I will remind everybody that cosine of pi is equal to -1. I'll give you a minute and a half. Let's see what's happening here. So f of 1, I'm going to plug into the middle piece because that's where x is defined to be equal to 1. That's going to be 4 cosine of pi times 1. Cosine of pi is -1, so we get -4. And then in a similar way, we know that the limit from the side of 1 that uses that same piece of the function, in this case, the side that's left of 1, you're going to get the same value. So the limit as x approaches 1 from the left of 4 cosine of pi x is also going to be -4. But then if we look at the limit as x approaches 1 from the right, if I plug in 1, I get 1 to the 17th plus the cube root of 1 plus 6, which is 1 plus 1 plus 6, which is 8. Which means the limit doesn't exist, which means the function can't be continuous because there's no way that the limit can equal the function value because the limit doesn't even exist. So I would say down here, f of x is not continuous at x equal to 1. And I usually like to say why. I would say because the limit as x approaches 1 of f of x does not exist. So now to answer the original question, where is this function continuous? Well, f of x is not continuous both at x equal to 1, and we also determined at x equal to -2. It is continuous everywhere else. So we would say that the interval continuity, the f of x is continuous on the interval from -infinity to -2, union -2 to +1, union +1 to infinity. Or in other words, at every possible value except for x equals 1 and x equals -2. So this function isn't continuous in 2 different spots for 2 different reasons. It's not continuous at -2 because the function isn't defined there. It's not continuous at +1 because the limit doesn't exist there. And the third way, which we'll see in this next example, that you might get a function to be not continuous at a point, is for the limit to exist and the function to exist, but for them not to be equal to each other. For example, maybe if I can move these pieces of paper. Oh, question or chat. Let's see what's in the chat. When completing the first 2 steps, when do you decide what equations to use for finding f of c? Sure. So the way I decide is completely based upon how the function is piecewise defined. So for this one here, right, when I was looking at 0, so when I looked at f of 0, I had to use the piece of the piecewise function where x is defined to be equal to 0. So that's how I get f of 0. I plugged into this piece here because that's where x is equal to 0. For the limits, when I did the limit as x approaches 0 from the right, well, this piece is when x is just bigger than 0. So I used this piece of the function 4 cosine of pi x when x is approaching 0 from the right. On the other side, when x is approaching 0 from the left, that means we're left of 0. So I need to use the piece of the function where x is left of 0 or less than 0, but immediately less than 0, right? It can't be like x is less than 2. That's not getting, or sorry, -2. That's not getting close to x being 0 from the right. And then for the other part, same kind of idea. When we were finding f of 1, we happen to be using the same piece of the function because, again, this middle piece here is where x is defined to be equal to 1. When I did the limit from the left, I used the piece of the function where x was less than 1 or less than or equal to 1. So I used the same piece again. When the limit as x approaches 1 from the right, I used the piece where x was just bigger than 1. So that's going to be the piece where x is greater than 1. That's how we're figuring out which pieces to use to find our limits and to plug in. Cool. Let's look at another example to kind of see the other way, the third way a function can fail to be continuous, which is, I'm going to make up, I've got another example. Let's say we have, that's great. Let's say our function is, sure. We have, so I will point out, and this is a pretty common problem. you don't really get discontinuity without using a piecewise function. Like there are some functions that are discontinuous. For example, actually, here's a good example. F of x equal to like the absolute value of x minus 2 divided by x minus 2 clearly must be discontinuous at what value of x? Show me on your fingers. Yeah, right, exactly. This is for sure not continuous at x equal to 2. It is continuous everywhere else. F of x is continuous on the entire real number line except at 2. So sometimes but even then, I'm kind of really just disguising a piecewise function here. The absolute value of x minus 2 is a piecewise function. We just encounter it so often that we've come up with notation for it, so we don't have to write out the whole piecewise function every time. But really, side note here, the absolute value of x minus 2 is just the piecewise function x minus 2 when x is bigger than 2 and negative x minus 2 when x is less than or equal to 2. So as I was saying, most of the time, if someone's trying to give you an example of something that's discontinuous, it could be rational, I suppose. But other than that, like really piecewise functions are our bread and butter of discontinuous functions. So let's look at another example here. Let's say our function g of x is equal to the piecewise function. Yeah, let's do that. Sine of 4x over 2x when x is not equal to 0. And let's say 4 when x is equal to 0. So let's go through our use. So again, I should point out, for the piece of the function that's defined everywhere except for 0, it is defined everywhere except for 0, meaning as long as I'm not plugging in 0, I'll get a value, right? Sine of 4 times anything will exist. It might be some weird value. 2 times anything that's not 0 will be not 0, and we can divide by not 0. This function is continuous everywhere except for 0, because it's continuous on its domain. So the only place we have to worry about is 0. So let's take a look. So first thing we check, what's f of 0 going to be? Well, they told us it was 4. Second thing we have to check, the limit. Now in this case, no, sorry, it's really hard to write G and then use, sorry, I meant to be writing G's here, not F's. Sometimes we try to use different letters just for the sake of seeing other things, and then we often forget. Okay, so I don't have to look at the one-sided limits here, because on either side of 0, it's the same piece of the function, right? Whether I'm looking at the limit as x approaches 0 from the right, well, if I'm approaching 0 from the right, that means I'm larger than 0, which means I'm using this piece of the function. Or I'm looking at the limit as x approaches 0 from the left, I'm still using this piece of the function. So since it's the same function on either side of 0, I don't need to look at the one-sided limits. Yeah. No, so I'll show you an example of that in a minute. Yeah. So this I would just write as the limit as x approaches 0 of sine of 4x over 2x. And then we have to remember how to evaluate this kind of limit. So I like using what I have called the wish method. I'm going to write this as the limit as x approaches 0 of sine of 4x over blank times blank over 2x. And then I'm going to fill in what I wish I had. Now, I'll remind you, we're always trying to make it so we have sine of something over the same something, or the reciprocal of that. You could have something over the same sine of something. But I don't want to fill in like a sine of 2x here and a sine of 2x there. I want to fill in the easier thing, meaning I just want to say, I wish I had 4x right there. But to have a 4x there, I also have to have a 4x up here. And then I think you can just find the answer at this point. The limit as x goes to 0 of sine of 4x over 4x is 1. And 4x divided by 2x, the x's cancel. And 4 divided by 2 is just 2. So the limit as x approaches 0 of sine of 4x over 2x is equal to 2. The function is defined to be equal to 4. Those numbers aren't the same. So we have here that g of x is not continuous at x equals 0 because f of 0 does not equal the limit as x approaches. It's not f of 0, g of 0 does not equal the limit as x approaches 0 of g of x. Right? G of 0 is 4. And the limit as x approaches 0 of g of x is 2. Yeah. Yes, sorry. Yeah. Anytime, please. Just you can do you don't need to raise your hand. If I need to move something, just say, hey James, can you move the paper? And I'll be like, yes, of course. I literally can see exactly what's being displayed up there right here. And I can see it's not on the screen. I just need to actually look at it every once in a while. I don't know like any of your, that's not true. I know like 2 of your names. Real quick, what's your name? Allie, I know Julio. What's your name in the hoodie?
Carson.
Carson, what's your name? Angie and Jeannie. I don't know your name. I feel like I should though. Jose, what's your name? Say that one more time. Aileen? Eileen. Cool. The reason I asked is because I want to say Carson, to address your question, right? It was Carson? Cool. I'll probably won't remember the names, but I'll try. It's easier than classes that meet 3 days a week. But that doesn't mean I can't do it. But to address Carson's question, he was asking about, well, what if we had something like f of x equal to x squared plus 4x minus 12 over x plus 6 when x is not equal to -6, and I don't know, 7 when x is equal to -6. Could we do the same sort of thing? And the answer is yes. This function, f of x, is defined to be this piece when x is larger than -6 and when x is less than -6. So I know that step 1, if I was looking at continuity, f of -6 would be equal to 7. Step 2, when I'm looking for the limit as x approaches -6 of f of x, I don't have to do the one side of the limits here either, because on either side of -6, the function is defined to be the same piece. So I can just say that the limit as x approaches -6 of f of x is the limit as x approaches -6 of x squared plus 4x minus 12 over x plus 6. And then I would try to plug it in. And if I do that, I'm going to get 36 minus 24 minus 12, which is 0, over -6 plus 6, which is 0. So that means I need to do something. I need to factor. So I'm going to factor. We have the limit as x goes to -6 of x plus 6 times x minus 2 over x plus 6. Sounds like there's a dog walking by. And then canceling or dividing the x plus 6's. We have the limit as x approaches -6 of x minus 2. And then we substitute in and get -6 minus 2, which is -8. Sure. So the reason we don't need, so normally, right, if you had something where x was like less than -6 and x was bigger than -6, you would need to do this. Really, this is kind of almost a lazy notation here. I could have just as easily written this function as x squared plus 4x minus 12 over x plus 6 when x is less than -6, 7 when x is equal to -6, and x squared plus 4x minus 12 over x plus 6 when x is bigger than -6. And I could use one-sided limits, but I'll point out, right, the one-sided limits, it's going to be the same work either way. The limit as x approaches -6 from the left, I'm going to use this piece, which is x squared plus 4x minus 12 over x plus 6. And the limit as x approaches -6 from the right is going to be the same piece. And they're both going to evaluate the same way. They're both going to factor the same way and cancel the same way. I'll be left with x minus 2 after I factor and cancel. And then I'm going to plug in -6 either way and get -6 minus 2 either way. So you certainly could write more things if you wanted to, but we don't need to. Yeah, exactly. Exactly that. If you have a not equals, you can assume that the function is the same function on either side of the thing it's not equal to. Yeah. So since I'm defining this function f of x to be x squared plus 4x minus 12 over x plus 6 when x is not equal to 6, that means I can assume safely that this function is this piece when x is greater than 6 and when x is lesser than 6. Right. Right. We don't need to do the one-side loss. Okay. Do one more example with continuity, then we'll talk. I feel like I didn't say much about limits of the type where you had not 0 divided by 0, like where the limit ended up equaling infinity. I feel like we didn't cover much of that. So I'll take a few minutes to talk about that. It's actually, there's not much to say about that, which is kind of nice. But let's do one more continuity example and the intermediate volume theorem as well. So here's a very, I think, pretty typical test type question. Find constants A and B so that the function f of x equal to 2x cubed plus 1 when x is less than 1, ax squared plus b when x is greater than or equal to 1 and strictly less than 3, and 4x minus 1 when x is bigger than or equal to 3, so that this function is continuous everywhere. So the only values of concern are x equal to 1 and x equal to 3. Because each piece here is a polynomial, right? You've got positive integer powers of x. When that's the case, every polynomial is continuous everywhere. So the only place we have to worry where this piecewise function might be discontinuous is when you switch from this piece to this piece and this piece to this piece. So we need to try and find the values A and B that are going to ensure for us that the limit from either side of the switchover points ends up being the same value. So I don't really actually need to find f of 1 and f of 3. I know there are going to be things that exist. Let's actually talk about the limits. So limits. To ensure continuity here, we really need both that the limit as x approaches 1 exists, and we also need the limit as x approaches 3 exists. I really should say the limit as x approaches 3 of f of x. It's more appropriate. For a limit to exist, the left-hand limit and the right-hand limit have to be the same. So what this means for us is that we need the limit as x approaches 1 from the left. Okay, which piece of the piecewise function am I going to use when I'm looking at the limit as x approaches 1 from the left side? The top piece, the middle piece, or the bottom piece? The top piece, because that's where x is left of 1. And that needs to equal the limit as x approaches 1 from the right. Now which piece am I using? Top, middle, or bottom? Middle. So I will point out that the bottom piece x is bigger than 1, but it's too far past 1, right? We're not just bigger than 1, we are right of 1, but getting closer and closer and closer to 1. So this is the piece where x is just to the right of 1 and gets as close to 1 as we need to. So that's the piece I'm using there. Evaluating each of these limits, I'm going to have that 2 times 1 cubed plus 1, so 2 times 1 plus 1 is 3, equal to a times 1 squared plus b. or a plus b. So I know that a plus b has to equal 3. That's not enough, right? That doesn't tell me what a and b have to be. They could be 3 and 0, or 6 and -3, or 20 million and 20 million and 3. Or no, the other way, -20 million, -20 million. Right? They could be all sorts of things. We need the other piece of information. So we also need the limit as x approaches 3 from the left. If I'm approaching 3 from the left, top, middle, or bottom? Middle, right? Because that's where x is left of 3 is going to equal the limit as x approaches 3 from the right, which is going to be the bottom piece that I'm going to use for that limit. What was that? Yeah, the bottom. Yeah, because that's where x is bigger than 3. X is bigger than or equal to 3. Yeah, question. Well, so when I took this limit, what did I do to take that limit? Right, and I got 2 times 1 cubed plus 1, and yeah, you're right. I didn't tell my work, right? But that's definitely 2 times 1 plus 1, which is 2 plus 1, which is 3. Same deal on the right hand side here. I plugged in 1 for x. 1 squared is 1. A times 1 is a plus b. Similar deal down here. I'm going to plug in 3. I'll show my work here more. So if I plug in 3, I'm going to get a times 3 squared plus b, which is 9 times a plus b. Here, I'm going to plug in 3. I'm going to get 4 times 3. I should have done that up here. Well, minus 1, which is going to be 12 minus 1, which is 11. So now I have 2 equations and 2 unknowns. I should be able to solve this system of equations. If it were me, I would do the following. So I have a plus b equal to 3, 9a plus b equal to 11. Yeah, sure. There's lots of ways to do this. I guess I would say b equals 3 minus a, and then plug that in for b down here, and then get 9a plus 3 minus a equals 11. 9a minus a is 8a plus 3 equals 11. 8a equals 8. A equals 1. And then going back over here, that means b is going to equal 3 minus 1. So b is going to be 2. So those are the values of a and b that guarantee this function is continuous. Now I will point out, I didn't actually check what the function value was at 1 or at 3. We could now, but it's kind of inconsequential. If a is, I know there's a chat there. I will look at it in just a second. If a is 1 and b is 2, and I plug in 1 for this function, if I plug in 1, I'm going to get 1 times 1 plus 2, which is going to be 1 plus 2, which is 3. So f of 1 is 3, just like the limit as x approaches 1 is 3. And similarly, if I plug in 3, f of 3 is 12 minus 1, which is 11, and the limit as x approaches 3 is also 11. So there's no issue there. Let's see what's in the chat here. Why do you use 1 and 3 and not 0 and 1? Well, for this one, I used 1 and 3 because those are the places where we're changing from one piece to another piece. We change from this piece to this piece at x equals 1, and we change from this piece to this piece at x equals 3. Basically, whatever values of x are where you switch from one piece to the next piece, that's usually where you have to look and make sure the limit actually exists. So that's pretty much most of what there is to say about continuity. Again, I will kind of reiterate, most functions are continuous on their domains. That's something I would move forward with. All the usuals, right? Polynomials, trig, rational functions, exponential functions, logarithmic functions, those functions are continuous on their domains. At some point, we'll talk about inverse trig functions as well. They're kind of wonky, so I'll prepare you for that. They're weird. Let's take a brief look at the intermediate value theorem, and then we'll talk about some more ones, I guess. What time is it? We got 30 minutes. Yeah. So the intermediate value theorem. And definitely we will revisit it when we talk about the mean value theorem later on. So the intermediate value theorem, almost always abbreviated as the IVT. I should say, not that it's abbreviated differently, just that it's almost always abbreviated. Like no one's going to write all that. So the general idea is that if your function's continuous on some interval, I'm gonna write this down in a second, but just hold on for that. And you go from, in fact, let's actually draw the picture before I say all the words. So let's say we've got some function that's continuous on an interval, let's say from A to B. The idea is that if your function is continuous on an interval, then you are guaranteed in that interval to be able to get every other y value between your left y value here. So there's f of a. And your rightmost y value here. Yes, I know I'm saying leftmost and rightmost. What I really mean by that is the y value you get when you plug in the left endpoint and the y value you get when you plug in the right endpoint. So what the intermediate value theorem says, and we'll write all the words here in a moment, is that I am able to get every y value in between f of a and f of b using some x value that came from between a and b. So for example, graphically, I said, like, here's some y value between f of a and f of b. I feel like the book usually uses, I don't even know what they use. N maybe? I don't know. I'm going to use y naught. That there has to be an x value between a and b that if I plug that x value into this function, it gives me that y value. Well, look, I'm going to go over here, find the point on the function, and then go down here. That x value, which we often call c, is between a and b, and it is true that f of c is equal to the y value that I have identified. This function, by the way, is f of x. So that's graphically what we're talking about. That if your function is continuous, you get all the y values between your two y values that you started with, your endpoint y values. Here's how we say it with the mathematical terminology. So if f of x is continuous on the closed interval AB, meaning the interval includes the endpoints, then it takes on or achieves every value at least once, but maybe more than once, between f of a and f of b. And that's the intermediate value theorem. Said another way, if f of a is less than some y, less than f of b, or in other words, if there's some y between your f of a and your f of b, there must exist at least one number c, and c had better be between a and b, such that f of c is equal to y naught, which is exactly what this picture is showing me. Importantly, the theorem does not tell you how to find c. All it says is that if your function is continuous, then you're guaranteed to get every y value between the two y values from some value c that's in the interval. But it does not tell us what that c value might be. Let's look at an example of how one might use the intermediate value theorem. A typical use of the intermediate value theorem is to show that an equation has a solution. For example, we're going to show that x cubed plus x minus 7 equal to 0 has a solution. It might have many. The most it could actually have is 3, because it's the 3rd degree polynomial. And you can have at most 3 zeros, but that's not what we're asked about. We're just asked to show it has a solution, at least one. So the first thing you almost always want to do with these is whatever thing you're trying to show is equal to 0, give that a name. Call it f of x or g of x or whatever your favorite letter function name is. So we're going to let f of x equal the thing that we're trying to show must equal 0 somewhere. The pretty standard first step. After that, if they're nice, they would have given us an interval. They weren't nice. They didn't give us an interval. So we're going to make one up. So to be able to be equal to 0, we are going to try and show that the function, well, first of all, actually, is the function continuous? It is. It's a polynomial. So we know that if it goes from somewhere that's below 0 to somewhere that's above 0, since it's continuous, it had to cross through the value, the y value of 0. AKA, it had to cross through the x-axis. So pick some numbers. Pick an easy number to plug in for x. I'm going to try 0. F of 0 is 0 plus 0 minus 7, which is negative 7, which is negative. Let's pick another number. Let's try f of 1. F of 1 is 1 plus 1 minus 7. Nope, still negative. How about 2? F of 2 is 8 plus 2 minus 7, which is 3, which is positive. Great. So here's what I would point out. This means graphically, I could actually plot these points, right? I mean, f of 0 is negative 7. F of 1 is negative 5. And f of 2 is positive 3. So these points are all on my curve, and the curve is continuous. So watch this. When I draw it, I thought I had a blueprint up there. Right, there's no way I can avoid crossing the x-axis if I'm going to go from that point there to that point there. And the function is continuous. I can't just jump over it. I have to go through it. So here's what this means for us. Since f of x is continuous, I usually like to say on the interval I'm going to use. I try to pick the smallest interval possible. So I could say it's continuous on the interval from 0 to 2, but I would feel like I was doing a better job if I said on the interval from 1 to 2. Right? Certainly continuous on the interval. And that's where we cross from being negative to being positive, somewhere between 1 and 2. So since f of x is continuous on the interval, and we have seen that f of 1 is negative and f of 2 is positive, then we can say by the intermediate value theorem, there must be some number c. And where does c have to live? What numbers is c between? Right. Between 1 and 2, because that's the interval I decided to use. There's got to be a number c between 1 and 2 such that f of c is equal to 0. Or in other words, c is a solution to x cubed plus x minus 7 equals 0. I don't think you really need that last part. I just want to make it clear. I think you can end right here just fine. Because, well, so I would like to, if I could be as precise as I'm able to be about where c is. So if I had said, since f of x is continuous on the interval from 0 to 2, and then f of 0 is negative and f of 2 is positive, then I would have said that my solution c had to live somewhere between not 1 and 2, but between 0 and 2. And that's a wider interval. I would rather pick a narrow interval to give more precision about where c lives. But that's all we can say about c. I don't know anymore. I know c is somewhere between 1 and 2. That's it. I don't know what c actually is. Solving this equation, although not impossible, It's something we don't really learn actually. Like we don't really learn how to solve. There is a way of actually like finding the solution to a cubic polynomial, but it's pretty advanced actually, surprisingly. Whereas everybody knows how to solve a quadratic equation, you use the quadratic formula. There is some sort of cubic formula, but it's based on a lot of like, you have to do this and this and like, there's a lot of steps. We do not find the solution, right? The question didn't say solve this equation. The question said show that a solution exists. Right, right. So that's why it's really important to read the question carefully. Right? If they say solve something, you actually have to find your x value. If they say show this a solution, then you don't have to find the x value, you just have to show that one has to be possible to find. Let's do one more like this. So another fairly common example is I want to show that cosine of x equal to x has a solution on the interval from 0 to 1. This one it doesn't require, but is much easier, and it's a standard thing to do if we make a first additional step. So before I start trying to say like what's f, whatever, you want to bring everything to one side of the equation. I don't want to be trying to solve or show that cosine x equals x as a solution. I want to instead, I'm going to show that cosine of x minus x equal to 0 has a solution on the interval from 0 to 1. And I'm going to let f of x equal the thing that I'm trying to show is equal to 0 somewhere. I would observe, I would just observe that function. Is that function continuous? It is. So I should mention, when you have continuous functions and you add or subtract them together, the result is also continuous. So cosine of x is continuous everywhere, y equals x is continuous everywhere, and their difference is also continuous everywhere. So this is continuous, which we'll use in a minute. We need to now, well, they gave us an interval here, so we're just going to plug in the points and see what happens. So let's look at f of 0. F of 0 is cosine of 0 minus 0, which is 1 minus 0, which is positive. I don't really care that it's equal to 1. I just care that it's bigger than 0. Here's where things get a little bit dicey. F of 1 is cosine of 1 minus 1. None of you should know what cosine of 1 is. I don't know what cosine of 1 is. 1 is, I should say, 1 radian is close to 60 degrees. It's like 57 degrees approximately. Right? Because 1 radian, I'll remind you, 1 radian is just, if you go 1 radian length, 1 radius is length around the arc of the circle. So that is about 1 radius, or 1 radian, and that angle is about 60 degrees, which makes sense, right? Because all the way around the circle, there's a little more than 6 radians. So all the way around the circle, each radian should be about 1/6 of the total angle measure, which is a little bit less than 60 degrees. And I know that cosine of 60 degrees is 1/2. Cosine of 57 degrees is a little bit smaller than that, but here's what I'm actually going to say. You know what 1 isn't? It's not 0. It's not 2 pi. It's not the angle where cosine is equal to 1. Right? If you're over here at this point here at 1, 0, the angle there is either 0 or 2 pi radians or 4 pi radians. And that is the place on the unit circle where cosine is the largest, where cosine is equal to positive 1. That angle isn't that angle. So that value has to be smaller than 1. Which means this whole expression is less than 1 minus 1, which is 0. Now, I feel like that's a little bit, what's what I'm looking for here? It's not always easy to see that. Like, this is not something that everyone's gonna be like, oh yeah, of course, like cosine of this is less than 1 times that. So if you can't use the endpoints they've given you to make it work, you can go smaller. You can say, well, I know I need to work within the realms of 0 to 1. So let's pick a number that's less than 1 that is easy to take a trig function of. So instead of using, well, I can't use pi over 3 because pi over 3 is a little bit bigger than 1. Right? Pi over 3 is 60 degrees, and we said our angle was a little bit smaller than 60 degrees. But we could use pi over 4. And if we do that, we can say that f of pi over 4 is cosine of pi over 4 minus pi over 4. Ooh, is this even going to work? I don't know. Let's find out. Cosine of pi over 4 is the square root of 2 over 2. Is this number negative? Good question. Let's get a common denominator. So I'm going to multiply this by 2 over 2. This is equal to 2 root 2 over 4 minus pi over 4, which is equal to 2 root 2 minus pi all over 4. All right. What's bigger, pi or 2 times the square root of 2? Good question. Well, here's something that's probably worth knowing. The square root of 2 is approximately 1.4. That's one that comes up often enough that you probably, it's kind of like knowing that pi is about 3.14 or the e is about 2.7. Square root of 2 is one of those other irrational numbers that you probably should have a good concept of. So square root of 2 is about 1.4. 2 times that is about 2.8. 2.8 is definitely smaller than pi, right? Pi is 3.14 approximately. So 2.8 minus pi is going to be a negative number. So that would also work. So now we can say, great, I know that f of 0 is positive. I know that f of pi over 4 is negative. I know the function's continuous on the interval. So I can say, and I will say when you're doing a intermediate value theorem problem, you really do need to write these words at the end of your problem. You can't just like write all this math and then be like, yeah, it is there. No, you should say these words. You say, since f of x equal to cosine of x minus x is continuous on, I'm going to use the smaller interval. I'm going to use the interval from 0 to pi over 4. And we just found that f of 0 is positive and f of pi over 4 is negative. Then there must exist, probably don't need the then part there. You probably just say there must exist. There must exist a number c. I always think you should say where c has to live. Where does c have to live between? Right, 0 and pi over 4, such that f of c is equal to 0. And that's enough. That means that this equation, cosine x equal to x, has a solution that's between x equals 0 and x equals pi over 4, which is certainly between x equals 0 and x equals 1, because pi over 4 is smaller than 1. And although we certainly use the intermediate value theorem in other things, like in other theorems later on, this is most of what we do with it from a student's perspective. Like these are the most of the kind of questions you get about the intermediate value theorem is that either like use it to show that there's something that some equation has a solution, or why does we also might ask like why does the intermediate value theorem fail here? And it usually either fails because the function isn't continuous or because the interval isn't a closed interval. All right, let's spend the last 12 minutes here talking about some limits that end up being infinite, which are, we might not even need the whole 12 minutes to be perfectly frank. It's really kind of 3 things can happen and they're pretty not terrible to see what happens. So let's look at some examples. let's say I want to find, so limits that are either infinity or negative, aka vertical asymptotes. That's what we're really talking about here, is vertical asymptotes. Okay, with one caveat. Let's say I wanted to find the limit as x approaches 3 from the left of 2x over x minus 3. Just like with most limits, I would start off here by substituting in the value that x is approaching. So here I'm going to get 6 over 3 minus 3, which is 6 over 0. Now, that's kind of problematic. It's not a 0 over 0. So it's not one of those situations where we're going to factor and cancel or multiply by a conjugate or get a common denominator. It's actually a lot less work than that. When we get to 6 over a 0, we know our answer is going to be one of 3 things: infinity, negative infinity, or does not exist. And really, that last one is only possible if you're looking at a double-sided limit. If you're looking at a single-sided limit that happens to be some non-zero number over 0, the answer is going to be either infinity or negative infinity. The only job we have is to figure out, is this thing positive or negative? Well, the numerator is definitely positive. So for one-sided limits like this, where when you plug in what x is approaching, you get a non-zero number divided by 0, the limit is always going to be either infinity or negative infinity. Let me show you what I mean, and we'll circle back around here. So here, we're approaching 3 from the left side of 3. So we're slightly smaller than 3. If you take a number that is slightly smaller than 3 and subtract 3, we end up with a number that is very slightly negative. So what I usually like to write for something like this is I would actually write this as limit as x approaches 3 from the left of 2x over x minus 3. And when I plug in that 3, the numerator is close enough to 6. I don't really care that it's like 5.99999 or whatever. But the denominator, I actually want to think of as not just 0, but I really want to think of it as a very slightly negative number, which I like to write like that. 0 with a negative superscript. It's not that I'm approaching 0 from the left, it's just that I'm slightly negative. So what we should imagine is something like 6 over negative 1/1,000,000th. That's a very small negative number on the bottom. But when you divide by a fraction, how do we actually do that? To divide by a fraction, we end up multiplying by what? Yeah. And the reciprocal of negative 1 over 1,000,000 is negative 1,000,000 over 1. And 6 times negative 1,000,000 is negative 6,000,000. So this is showing us that, oh yeah, if the denominator is really small, this fraction gets really exceptionally large. It happens to be, in this case, negatively large. So this limit is negative infinity. Now, in practice, all you really have to do is observe that you have not 0 divided by 0, and then just figure out, is the overall thing positive or negative? Here, I had a positive divided by a negative, so the overall sign was negative. If I approach 3 from the other side, so limit x approaches 3 from the right of 2x over x minus 3, I still get 6 on top, but now a number slightly larger than 3 minus 3 is going to be very close to 0, but on the positive side. So now my fraction is a positive number divided by a positive number, which is going to be positive infinity. Now, a couple things here. Do either of these limits actually exist? No. The limit as x goes to 3 from the left of 2x over x minus 3 does not exist. And it also happens to get really, really negative as we approach it from the left. So we like to be more inclusive with our answer. We're gonna say, oh yeah, I know it doesn't exist, you know it doesn't exist, and also we both know that the function gets very, very negative on the left side of 3. Similarly, on the right side of 3, the limit also doesn't exist, but the function gets really, really positively large on the right side of 3. And then if someone did ask about the two-sided limit, we would say that the double-sided limit as x approaches 3 of 2x over x minus 3. Since the left side and the right side are doing different things, we would say that that limit does not exist. We can't even say it's infinity or negative infinity because they're not going to the same direction. Graphically, here's what's going on. We have a vertical asymptote at x equals 3. And we can see that as we approach 3 from the right, the function goes up to positive infinity. And as we approach 3 from the left, the function goes down to negative infinity. So that's how that looks. So when you have the limit as x approaches a real number, a finite real number, not infinity or infinity, but if the limit as x approaches 3 is either infinity or negative infinity from either side, that means you have a vertical asymptote. And maybe you have something like this if they're going different ways, or like this if they're going the same way, or like this if they're going the same way. So we got time. Another example, just to, oh yeah, question. Let's look at the next example, which is exactly the question you're asking. Good question. So for example, if we had the limit as x approaches -2 of 5x over x plus 2 to the 4th. Sorry, -2 from the left. Well, if I plug in that -2, I'm going to get -10 on top. Being left of -2 means you're more negative than -2. So it's like, I'm thinking of like -2.1. -2.1 plus 2 is very, very slightly negative. So I have a very, very small negative number, but then it's being raised to the 4th power. And anything to an even power is going to end up being positive. So this is really a -10 over a slightly positive small number, which is then going to be a negative divided by a positive, which is negative infinity. And what we're also going to see is the same thing happens on the other side of 2. If I look at the limit as x approaches, -2. Limit as x approaches -2 from the right of the same expression. Now, when I plug in -2 for x, I still get -10 on the top. And the denominator, a number a little bit larger than -2, or on the right side of -2 is -1.9. -1.9 plus 2 is slightly positive. But then it doesn't really matter because I'm raising it to the 4th power, so it would have been positive even if it wasn't. And then, once again, a negative divided by a positive is, in fact, negative. And then, yes, if someone asked us what's the two-sided limit, we would say that the limit as x approaches -2 overall of 5x over x plus 2 to the 4th is negative infinity. Because the left side and the right side are both going downwards towards negative infinity. Graphically, this would look like a vertical asymptote where both sides were going down. So I have a vertical asymptote at -2. And then on either side, I'm going down like that, down like this. Fun fact, this graph does have a horizontal asymptote at y equals 0, and this graph does cross its horizontal asymptote at the origin. This is totally allowed. I really want to emphasize, just so you all are aware, graphs can cross their horizontal asymptotes. It is totally valid. A horizontal asymptote is really just asking you what's happening to the function as you go way, 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 way to the right or way, way, way to the left. But it doesn't really care what goes on in the middle. And since, yeah, we got 2 minutes. We might as well mention it here. I'll just point out that to find the horizontal asymptotes, instead of wanting a limit as x approaches a number to equal infinity, It's kind of the opposite. You take the limit as x goes to infinity and you ask, what does the function do? So here, if I take the limit as x goes to infinity of 5x over x plus 2 to the fourth, that's kind of terrible. Top's going to infinity, bottom's going to infinity, but the denominator is a quartic, a fourth power of x. It's going to dominate the numerator. If you really, really wanted to, even though I don't, you could multiply it out and say you have 5x over x to the fourth plus 8x cubed plus 24x squared plus 32x plus 16. I'm pretty sure that's how that multiplies out. And then the highest power is the first here, highest power is the fourth here. You could divide everything by x to the fourth and write it as the limit as x goes to infinity of 5 over x cubed over 1 plus 8 over x plus 24 over x squared plus 32 over x cubed plus 16 over x to the fourth. And then everything that's being divided by x to a positive power, as x gets really, really large, all those things are going to get really, really small. So we end up with 0 divided by 1 plus 0 plus 0 plus 0 plus 0, which is 0. So as x goes to infinity, and you could also say as x goes to minus infinity, because the same thing would happen, this function gets closer and closer and closer to 0. So we have a horizontal asymptote of y equal to 0. Which makes sense if you think about it, right? If you plug in a really big number for x, if you plugged in 1,000 for x, the numerator would be 1,000, and the denominator would be 1,000 to the fourth power, which is what? A trillion. 1,000 divided by a trillion, super duper small. And it just gets smaller and smaller as x gets larger and larger. So to sum up, if the degree in the denominator is larger than the degree in the numerator, and x gets really, really large, the overall fraction gets closer and closer to 0 because the denominator outpaces the numerator. We'll talk more on, what, Tuesday? When we meet again? Yeah, Tuesday.